Now we see this question. 2 point charges Q and minus Q are located at points 0, 0, minus A and 0, 0, plus A respectively. Minus Q and plus Q, 0, 0, minus A and 0, 0, plus A respectively. That means minus Q is at minus A. Two point charges plus Q and minus Q. Okay. That is plus Q at 0, 0, minus A, minus Q at 0, 0, plus A. Two point charges plus Q and minus Q are located at points 0, 0, minus A and 0, 0, plus A respectively. That is plus Q and minus Q placed at 0, 0, minus A, 0, 0, plus A. Note that plus Q is at 0, 0, minus A and minus Q is at 0, 0, plus A. Okay. Find the electrostatic potential at 0, 0, Z and x, y, 0. X, y, 0. Actually, the sum seems to be somewhat complicated, but you can do it easily, provided you know how to handle with the axis. Okay, because you see here lot of zeros are there, so somehow intuitively you can feel that problem should be simple to handle. So the charges are at 0, 0, minus A and 0, 0, plus A. That means along Z axis. So it's better you draw the coordinate axis like this. Okay, okay, X, Y, Z. It will be easier. Plus Q at 0, 0, minus A. This is plus Q. Minus Q at 0, 0, plus A. This is minus Q. This is Z axis. This is X axis. This is Y axis. It's a three-dimensional way of showing things. The plane of the diagram is XOZ plane. Y axis is towards you. First one, potential at 0, 0, Z. Also potential is at x, y, 0. 0, 0, Z, somewhere here. 0, 0, Z means that point should have x coordinate 0, y coordinate 0, z coordinate z. So you see it is an axial point. This is 2a, this is a, therefore this is minus a, 2a is the dipole length. So it is basically the point P is on the axial line. So use the formula potential due to a dipole on the axial line, not the far off point case. Take the point, not the far off point case, general, applicable to any point. So the point P may be shown here. The reasonable assumption is, say Z is from O to P, Z, this coordinate, assume it to be greater than A. That means you can take the point P to be at an axial point of the dipole. Okay? Reasonable assumption. Otherwise you have to do accordingly. Right? So let's say that Z is this axial point, electrostatic potential, and this also the point is close to minus Q. So the formula for potential minus Kp by d square minus a square, instead of d it is Z here. P is 2aq. The minus symbol will come because the point is close to minus q, which is V is equal to minus P is 2aq for k, denominator 4 pi epsilon naught z square minus a square. Okay. The second case here, the point is x comma y comma 0. That means the point lies in the x or y plane. Infinite number of such points are there possible, but for all such points you will have z coordinate 0. So it should be in the x or y plane. Okay, for any point on the xy plane, any point on the xy plane will be an equatorial point for this dipole. Say this is the xy plane, means this is z axis. So all the points will be equatorial points on this xy plane. Therefore, potential will be 0. At any point on the at an equatorial point, the potential due to a dipole is 0, whether distant point or close by point. So for this, the answer is 0 volt. For this, the answer we minus 2aq by 4 pi epsilon naught z square minus a square. The subdivision B, what is the work done when you move a test charge from 5, 0, 0 to minus 7, 0, 0? Moving a test charge from this point to this point. Again you see this to this, 0 and 0, the point is having 0 and 0. Equatorial point. First you concentrate on this. Or you can say, see here, take this point. This x comma y comma 0 is 5 comma 0 comma 0. That is y is 0. So here the potential is 0. Again this one also potential is 0. Potential difference will be 0. Work done will be the charge into the potential difference. So 0 joule. These two are specific points corresponding to this x comma y comma 0. This y will include 0 also. This x can also will include 0. But you see the last one is 0 for both cases. Okay. Actually 5 comma 0 comma 0 means here somewhere. Minus 7 comma 0 comma 0 means x coordinate is also, x coordinate is minus 7, y coordinate is 0. So the 2 points are on the x axis. So you are moving a test charge along x axis. That's what the question itself says. Along the x axis. That is equatorial point from one place to the other. 0 joule, because potentials are 0 at each point. Subdivision C, instead of along x axis, if it is in any other path, is there any change in the answer? How would your answer change? There won't be any change, because the electrostatic field is a conservative field. Work done does not depend on the path, but depends on only on the terminal points. So if you shift a point or move a point from this point, move a test charge, if you move a test charge from this point to this point, irrespective of the path, work done would be 0. Okay, irrespective of the path. Then, if the above point charges are now placed in the same positions, say at A and B, but you apply an electric field such that it produces a case of unstable equilibrium. Okay, what will be the potential energy? So you know potential energy formula, U is minus P dot E. Unstable equilibrium potential energy should be maximum. Actually this is minus Pe cos theta. Maximum value of this will be there equal to Pe, that is theta should be 180. Cos 180 is minus 1. So Pe will be maximum potential energy in the that will correspond to unstable equilibrium. Potential energy should be maximum, but P is 2aq, therefore the answer for the potential energy 2aq into E. P is 2aq. This is maximum potential energy. That will only correspond to unstable equilibrium. Answer 2aqe. 2aqe. We will see how to derive the expression for electrostatic potential due to a dipole. Case A, at an axial point. P is an axial point, this is a dipole. AB is an electric dipole. C is just the center of the dipole, just to measure the distances. Okay, C is midway between A and B. Actually, when the dipole is too small, this won't be necessary. Okay, yeah. How to find the potential at P due to this dipole? Use principle of superposition for potentials. Find potential at P due to plus Q. Find potential at P due to minus Q. Find the algebraic sum, not vector sum, because potential is a scalar. Okay, let's see how to proceed. Potential at P due to plus Q. It is kq by r. R means this distance. So d minus L. 2L is the length of the dipole. So d minus L. Similarly, potential at P due to this minus Q, minus kq by d plus L. Distance of P from A. Therefore, net potential V will be equal to V1 plus V2. kq by d minus L plus, actually plus, but V2 itself is minus kq by d plus L. Simplify. kq 1 by d minus L minus 1 by d plus L. kq, note that k is 1 by 4 pi epsilon naught. Okay, d plus L minus d plus L by d square minus L square. This d will go off. K 2L into Q, 2LQ by d square minus L square. So net potential K into P by d square minus L square. P is electric dipole moment of the given dipole, which is 2L into Q. 2L is the dipole length. Q is one of the charges considered numerically. So Kp by d square minus L square. Suppose the point P is this side. You can proceed in a similar way, but you will end up with having minus Kp by d square minus L square. The point is closer to the negative charge. Okay. Then suppose if the point P is far off, distant point, that is d very much greater than L. L square is neglected in comparison with d squared. So V is equal to Kp by d square. For a distant point or for a short dipole or for a point dipole, V is Kp by d square. This is axial point. Okay.